Cristobal Correa has been at the forefront of innovative design for years, leading projects designing tension structures, art installations, long-span structures, stadiums and temporary buildings. Shown here are a selection of the most recent projects he's been involved in. He was educated at the Universidad de Chile and MIT before he joined Bureau Happold in 1998 and is now an associate principal in New York. Since 2012, Cristobal has been the Director of Technology at the Pratt Institute School of Graduate Architecture and Urban Design. He is also an active board member of Open House New York. One project he has led is the Crystal Bridges Museum of American Art in Arkansas, USA. It consists of 7 pavilions set floating on a ravine surrounded by native Ozark forest. The original natural creek was adapted into 3 ponds which flow beneath the buildings. The museum aims to bring people, art and nature together, which is celebrated through the structure as well as the contents. These structures consist of concrete bases, timber glulam arches, hanging steel cables and glass facades. The project shows the application of bridge design to building structures. Bridge construction methodology was adopted in order to create the floating nature. This is furthered through the suspended roof structure. The geometric shape of these roofs was governed by the structural performance. This suspended roof allowed for lighter glass facades with no internal structure to allow for an open space while providing views of the surrounding landscape to play up the interaction between architecture, art and nature. The surrounding environment embodied the building from incorporation of the stream and forest to use of the surrounding ground properties. The museum extends into the forest, so the user's experience from outdoors to indoors was a key factor. The design aimed to create clarity and ease for the circulation of visitors to experience the contents inside both the series of structures and within the forest itself. Building over the stream was a large driver for adopting a bridge construction due to various factors. One main challenge was the water leakage risk of building within a stream. The structure was also to act as a weir to aerate and purify the water in the pond and control the flow. The use of local materials was also key to this design. The large volume of timber was used from local pines found in the area. It was also key to use these materials in the most efficient way. For example, using steel cables, which is extremely strong in tension in order to reduce the volumes of other materials required. The timber roof structures adopt catenary arc shapes, which are very efficient in supporting loads. Each arc has a unique inner and outer radius for an optimised design. Sustainability was a key driver to this project. Locally sourced timber and efficient use of material was designed, but there was also a large volume of concrete used to support the structure. Using estimations and assumptions into the member sizes and material properties as shown, the total embodied carbon of one bridge structure is around 800 tonnes. This equates to 800 kilograms per metre squared of operational space. The timber is created in unique shapes that would be hard to reuse at the end of the building's lifespan. Hence, carbon storage in the timber has not been assumed, as the carbon is likely to be re-released in the future. Transportation has not been included, but would be a small percentage of this due to local materials being sourced. The chart shows each main material's impact on the embodied carbon. As you can see, concrete is a large proportion of this impact. Operationally, the building has a large open space with a high roof and a high percentage of glazing, making it thermally light. Heating and cooling would be at high cost to keep indoor environment constant with outdoor temperatures ranging between 0 and 40 degrees over the year. Including insulation panels and reducing the glazed area would decrease the operational carbon impact, but would also compromise the architectural vision. To reduce the volume of concrete, a few optimisations could be considered. The abutments supporting the roof structure are large due to the shear forces in the concrete. The use of cable ties could be used again, as used within bridge structures. As shown, this puts concrete into pure compression, which is where it is most efficient, with steel cables taking the tension with a small cross-sectional area. A thick concrete slab is required to span the lengths between legs. The number of legs could be optimised to reduce the material required. The slab itself would have varied loading between supports and midspan. Ribbing or optimisation of the material due to the stresses can reduce this volume. The concrete mix could also be optimised with the use of recycled aggregate and limestone from the area. Within the roof structure, although it looks predominantly timber, there is a lot of steel required to achieve the stability. Further innovation into this component could reduce the carbon impact considerably. For example, increasing the timber member sizes in order to reduce connections required. With these changes, the embodied carbon could be reduced to 430 tonnes, which is a 45% reduction. To further this reduction, a life cycle assessment could be undertaken to determine a new use for the timber elements after the structure's lifetime, With carbon storage assumed, a further 80% reduction in embodied carbon is estimated. Thank you for listening.